So if your organization operates in a world with serious variables, logistics, supply chains, finance, the headache. You can spend millions on these amazing optimization strategies, maybe using fixed rule models or classic forecasting, only to see them just shatter.
Yeah, the moment reality hits.
Exactly. A sudden port closure, an inflation shock, or, even just a big storm, and that whole meticulous plan is just, it's obsolete.
It is. And that reliance on static models isn't just brittle, it's a massive opportunity cost.
Mm.
The real issue is that traditional methods, they treat unpredictability as something to block, to mitigate.
Instead of learning from it.
Precisely.
Yeah.
Not an internal variable to learn from. And what we're seeing now, what our sources are all pointing to, is that reinforcement learning, or RL, is completely flipping that paradigm. It's the AI technique that lets systems make real-time, adaptive decisions because of that volatility, not in spite of it.
So our mission for this deep dive is to give you the fastest path to the core ideas here. We've gone through the research to show you exactly how RL moves planning away from those rigid rule sets and into something, well, truly dynamic, a framework that adjusts to everything from flash floods to market swings. So let's dive into what makes this so transformative. Okay, we have to start with the basics. For anyone listening who's tracking this field but maybe hasn't, built an RL agent themselves, how do we define reinforcement learning crisply?
Right. At its heart, RL is a type of machine learning where we have an agent that we put into an environment. And this agent, it learns to perform a series of actions, all in the pursuit of maximizing some kind of long-term reward.
And it's a loop, right?
It's a continuous loop. The agent acts, the environment gives it feedback, a reward or a penalty, and then the agent updates its internal strategy. We call that its policy.
And that update mechanism, the policy part, that feels like the critical difference. I mean, most people are familiar with supervised learning, where you just feed a model a bunch of labeled examples. You basically give it the answers.
That's a great way to put it. Supervised learning needs a human to label huge data sets first. You have to spell out exactly what good looks like. RL, on the other hand, it kind of operates in the dark. It doesn't need pre-labeled data at all. The agent learns purely from trial and error.
From experience.
From experience, yeah. It gets a simple numerical signal, the reward, right after it does something. And this learning by doing approach,
Yeah.
that is why it excels in these chaotic environments where the rules are always changing.
Okay, so let's focus on that flexibility. What can an RL agent do that, say, a traditional simulation model just completely fails at when faced with true random unpredictability?
Well, traditional models often work with these preset rules, these heuristics, or they run these massive simulations that assume things are, relatively stable.
Or at least predictable.
At least predictable, right? They assume a certain distribution of outcomes.
Mm.
But RL is designed for what we call stochastic environments, where randomness is just baked into the system. Its real power is in synthesizing failure. When a traditional system fails, a human has to go in and recalibrate it. When an RL agent gets a penalty,
Learns.
it immediately incorporates that negative signal into its policy to make sure that mistake is less likely next time. It's almost purpose-built for real-time risk mitigation.
That idea of synthesizing failure, that leads us right into the applications. This is where the value really shows up. Let's start with the physical world, weather and logistics.
Oh, this is a perfect example. Because the environment, the weather, is the very definition of a volatile, nonlinear system. So in transportation and agriculture, you're seeing RL systems being used to manage supply chains that are just constantly under threat from, well, the weather.
So walk us through it. What does that look like for something like a big delivery fleet?
Sure, an RL system that's managing a fleet isn't just finding the shortest route. It's treating time, fuel, and weather volatility as part of the total cost of any action.
Huh.
So a traditional system might see two routes, A and B, that are the same length, and it just picks one, maybe A.
Okay.
But the RL agent, having learned from millions of simulations or past real-world events, knows that Route A tends to flood during heavy rain season.
Ah.
So the system learns the optimal stochastic path, the one with the highest probability of success, of reward, even when things are uncertain.
And let's connect that to the business side. What is the reward function actually trying to maximize in that logistics scenario? What's the goal?
It's not simple, which is what makes RL so powerful. It's usually a compound objective. The agent might get rewarded for saving fuel,
Okay.
penalized for delays, and then heavily penalized if the whole fleet is down because of the storm. And crucially, the function is usually set up to maximize the long-term expected return, not just the success of one single delivery.
So it's not making short-sighted decisions.
Exactly. That prevents the agent from doing something that seems good now, but hurts the whole network later on.
And that framework seems to translate perfectly into our second big application, market adaptation. I mean, if weather is one kind of chaos, markets are something else entirely. Faster, more opaque.
Absolutely. In volatile markets, businesses are using RL for their core strategies. Dynamic pricing, managing inventory, production schedules. The agent's goal is to constantly adapt to shifting demand, what competitors are doing, and just, the big macroeconomic picture.
I think the clearest example for most of us is dynamic pricing online. How is an RL approach to pricing different from, say, a simple price matching bot?
It's a lot more sophisticated. A traditional system might have a simple rule like if competitor X drops their price by 5%, we drop ours by 4.
Right, very reactive.
Vary. An RL agent, though, it understands the consequences of that action. It learns that, sure, dropping the price might get you a quick sale, a short-term reward, but if you do that over and over, you might devalue your brand or start a price war, which tanks your long-term cumulative reward.
So what kind of complex variables would that reward function for a pricing model be juggling then?
It has to balance a lot of things.
Yeah.
It's often designed to maximize total revenue and customer retention while also minimizing things like having too much stock or running out of stock.
A balancing act.
A huge one. For example, the agent might get a high reward for a high-margin sale, a medium reward for a sale that grows market share, and a penalty if a customer buys something expensive and then immediately returns it.
Because they found it cheaper somewhere else.
Exactly.
Yeah.
That's a clear signal of dissatisfaction. The RL agent learns to balance all these conflicting goals to find an optimal adaptive pricing policy that older models just can't touch.
Okay, so if the agent is constantly processing all this, adjusting its strategy in real time, let's pull back the curtain on how it actually works. This is the how part of the deep dive. We're not talking about a job that runs overnight.
No, not at all. The core strength is the agent's ability to maintain and update its policy function while the environment is live. See, unlike traditional optimization, which often has to, restart the whole calculation when something changes, the RL agent is always in that cycle. Action, observation, reward, update.
And the speed. If the environment is changing in real time, a competitor changes a price, a sudden traffic jam, how fast is that policy actually updating?
That's where the computational needs come in. The policy itself might be a big neural network. The initial training takes a ton of power, but once it's deployed, the decision-making in the moment, the inference, it's almost instant. And on top of that, the agent is constantly dealing with something we call the explore versus exploit dilemma.
Okay, what's that?
In any given moment, the agent has to decide, should I exploit my current best strategy, the one I know works, for a guaranteed reward, or should I explore a new, different action that might lead to an even bigger reward but also carries risk?
So it's balancing safety versus discovery.
Perfectly put. And good RL algorithms manage that balance dynamically. It ensures the system stays responsive and doesn't get stuck doing something that's good, but not great.
That's a critical point. It means the agent isn't just waiting for a developer to give it new rules. Its policy is genuinely self-adjusting.
Precisely. And that's essential for navigating what we talked about before, the incredible space complexity of a market. Just think about all the possible combinations of prices, inventory levels, competitor moves, news events. It's a space that's way too vast for humans to write rules for. RL uses techniques like deep Q learning to approximate the best action across millions of possibilities, and it does it in real time.
So the outcome for you, listening to this, is pretty clear. This flexibility totally changes what organizational resilience means. You're moving from plans that assume things will be stable to a system of continuous data-driven adaptation that expects and absorbs shocks. Now, as amazing as this all sounds, we have to do the reality check. Deploying advanced RL, it's not a simple software upgrade. Our sources were very clear that implementation has some major hurdles.
Yeah, that raises the big question, right? If RL is so powerful, why isn't every company using it? The sources point to 4 main barriers, and they are significant. First is just raw computational power. To train these agents, you have to run massive simulations, millions and millions of interactions. That's incredibly resource-intensive. For a lot of companies, it's cost-prohibitive.
And the data itself, even if it doesn't need labels, it still has to be good, right?
It has to be exceptional. That's the second hurdle. You need high-quality, reliable data, a continuous, clean, high-velocity stream of it.
So market prices, user clicks, weather data.
All of it. If your input data is spotty or biased or just noisy, the learning process will fail. Or even worse, the agent will learn a deeply flawed, and very expensive policy.
And finding people who can actually build these things can't be easy.
That's the third challenge. You need specialized expertise. RL is one of the most technical fields in AI, designing the reward structure, tuning the parameters. It requires top-tier data science talent. And that talent is very scarce and very expensive. And finally, there's the practical challenge of just integration. The agent needs real-time data and needs to act fast. Plugging that kind of dynamic system into older legacy IT infrastructure can be a massive technical and security nightmare.
Let me push on one of those points. You mentioned the pricing agent needs to avoid short-term greed. But how do you actually stop it from doing that? How do you build a reward function that prioritizes long-term strategy?
That is probably the single hardest problem in designing an RL system. It's called the credit assignment problem. You have to design the reward function to look into the future, using techniques like discounted future rewards. If you only reward the immediate sale, the agent will act greedily.
So it's about delayed gratification.
It is. The solution requires that expert designer, that scarce talent we mentioned, to model penalties or rewards that might not show up for thousands of steps. You're essentially forcing the agent to prioritize strategic stability over just getting an instant win. It's a real art.
So wrapping this all up, what's the big picture here? We're looking at tech that can give a real competitive edge, but only if you can clear those hurdles.
That's the core takeaway. Reinforcement learning has immense, proven promise for truly adaptive planning, especially in industries that are just defined by constant change. It lets organizations translate their strategic goals into mathematical functions, leading to not just more efficiency or cost savings, but to fundamentally greater resilience in the face of, well, uncertainty.
And as the cost of computing keeps falling and as good data becomes more and more accessible, the role of RL is only going to grow. It'll move beyond just the giant corporations. It's going to fundamentally redefine how every organization manages volatility. Which brings us to our final thought for you to think about. We've talked about huge fleets and global markets, but think about your own highly variable world. If you could define the optimal long-term reward for one dynamic process in your daily life, maybe optimizing your household's energy use, or even navigating your career path, what would the variables and the penalties look like in your personal reinforcement learning policy? What would that policy function be trying to solve for? We'll catch you on the next deep dive.